We continue talking about the key point detectors and descriptors. Why we talk about this stuff here? This stuff is a little bit boring for you, right? But it's really important to understand what the key points, what the key point detector, what descriptors, and later in the complex code, it's really large code. You can see people use key point detector and descriptor to build up the CAS system, collision avoidance system, to predict, to measure the time to collision to preceding vehicle, right? Last video, we already know a little bit about the key points on the image, how to get the key point on the image. And our task right now is to find the key point in a sequence of the image that we can use to compute the time to collision to the preceding vehicle. So we need to robustly assign key point to its order based on some measure similarity. Right now we find the key point right here on this image, and how we find the similarity points in this different frame. We find the matching point together. Okay, that's the descriptors. So descriptors help us to assign similar key points in different images to its order. Right? A set of the key point in the one frame is assigned key point to another frame, such as the similarity of their respective descriptor is maximized, and the key points represent the same object in the image. So a good descriptor should be able to minimize the number of mismatch and avoid assigning the key point to its order that do not correspond to the same object. Sometimes they have a mismatch point right here, but the good descriptor they have to find correctly the similarity points on the frame by frame right here, and from that you can measure the time. Okay, that's the purpose of the descriptors. So here we have the two kinds of the descriptors. First one, we talk about the HOG descriptor, and SIP is the one of the algorithm use the HOG. So HOG stands for histograms of the orientation gradient. So the basis behind HOG is to describe the structure or object by distribution is intensity gradient in the local neighborhood. So to do that, an image is divided into cells with which gradients are computed and collected in the histogram. The set of histogram from all cells is then used as a similarities measure to uniquely identify an image patch or object. So when the algorithm use HOG right now is that we talk about the SIP. SIP stands for scale invariant filter transform. Later we had to practice the SIP into the SIP level code. So the SIP methods include both key point detector as well as the descriptors, and follow 5 steps right here. The first one, you have to key points had to detect it in the image. Okay. The second one, the key points surrounding areas is transformed by removing the orientation and thus ensure the canonical orientation. So the size of area is resized to sitting by sittings, provide normally patch. We have the key points right here of this patch right here. And third, we have to orientation and magnitude of each pixel within a normalized patch are computed based on the intensity gradient ES and EY. IS and IY. You have this patch, this area, there the sitting divided into sitting and sitting pixels right here. And then the orientation of magnitude of each pixel within a normalized patch are computed, okay, based on the intensity gradient, okay. For the normalized patch is right here we have this batch, and we had to divide into grid of 4 by 4 cell. We had to divide many cells right here by 4 by 4. So within the each cell, the orientation of the B cell with its threshold are collected in histogram consist of A bin. Right here we have the batch right here, this area. A lot of key points. Right now we have the 16 by 16 visual. We have to divide this patch into the 4 by 4 cells, 4 by 4, right? And each cell right here you have 1, 2, 3, 4, 5. Okay, so you have the A bins histograms of the 16 cell right here are concatenated into one 28 dimension vector. So each cell they got the value, they check the visual in each cell right here. If they have more than the threat value they collect right here. They say within each cell the orientation of the B cell with exceed a threshold or magnitude are collected into histogram consist of A bin. It means they will run all this cell and they got the value they put into histogram in A bin. For each cell they have the histogram. So the SIP detector's descriptor are able to robustly identify objects even amongst clutter and under partial occlusion. So the SIP detector, they use the HOG, and they're very good for identify the object. Okay, but the advantage of SIP is the low speed. Okay, which prevents it from being used in a real-time application, for example, on smartphones. So the other in HOG, not only that we have the SIP, we also have the surf or glove. They optimize the speed. Right here, SIP is low speed, right? So. And one more thing is right here, too computationally expensive, and it should not be used in the real-time application. SIP and surf heavily patent. It means it's not free for using. If you want to practice it, you have to write on the code OpenCV2 non-free. I will have another video talk about this, how you want to use SIP to get the descriptor or the detector. You have to include this one non-free because it's not the free on the market. You have to use this one to use SIP. So we have to know how to install the OpenCV for the Visual Studio 2019. I have another video to help you to understand. Right here you can see right here you will have the sums. You had to sum the error when you write the code. You include this one into the code, but you had to install the OpenCV. I will show you how to do that in another video. It takes a little bit of time to install that. We have to use the CMax to build up this library. Okay, talk later. Right now we already know about the HOG. So a much faster and free alternative is to the HOG. Is the family of binary descriptor. Okay, right now we have another one to process faster than the SIP. Okay, is the binary descriptor. Okay. So what the binary descriptor? Binary descriptor is different HOG. Okay, binary means 0 and 1. You're thinking about that, right? The HOG-based descriptors are based on the computing the intensity gradient. You have to remember the HOG, they based on the intensity gradient. Okay, and they're very cost operation. Even though some improvements such as surf you integral image instead, and this method don't lend themselves in the real application. Okay, in another way, binary descriptors is rely on the intensity information to encodes the information around the key points in a string of the binary numbers. Remember, in a string of binary number, which can be compared very efficiently in the matching step when the corresponding key points are searched. So in the binary descriptors, we have several algorithms. Use this one, but brief, brick, or RP and freak, KC. We will try all this one in the code later. Okay, that's they use the binary descriptor. We don't use the hash. Okay. Last time we mentioned right here is the hash. Right here we mentioned binary descriptor. Remember that. So the binary descriptors consist of three major parts. Right now it's a little bit confuse you, but it's not important. So let's understand it basically, and into the code is quite simple, more simple, more simpler. Okay, the first step is sample patterns, which describe sample points are located around the location of the key points. The second methods for orientation compensation, which remove influence of rotation of image paths around the key point location. A method sample pair selection, which generates a pairs of sample points, which are compared again to its order with regard their intensity value. So, with the first value is larger than the second, we write 1 into the binary string, and other we write 0 after performing these all points pairs in the sample pattern. A long binary chain is created. Okay. Right now we use the this methods brick. Okay, it means binary robust invariant scalable key points. Thus, the key point detector and descriptors is used to present for the binary descriptor family. So right now we don't talk about the brick, but use the binary descriptor, right? So we have now the methods right here, but we only talk about the a little bit the algorithm brick, how they apply the binary descriptor into brick. Okay. So the sampling pattern bricks is composed number of sample points. We have the patch right here. We have the number of points, the green one right here, and we have the concentric ring around the point, around the sample points. That is the area where the Gaussian smoothing, look like what we mentioned last video, is applied. So the sample pattern right here is fixed. Smoothing is important to avoid an effect that the core different signal to become extinguishable. Okay. We have the batch, we have the sample points, we have the concentric ring. Okay. So during sample pair, the brick algorithm differentiates between a long and short distance pair. Long and short distance pair. The long distance are the used for estimate the orientation of the image patch from intensity gradient, whereas the short distance pairs are used for intensity comparisons with the descriptor string is assembled. So right here, you can see we have patch right here. We have the sample point right here. Now we have the calculate the long distance pair and the short distance pair. Okay, we have the set. This is a mathematical. We can write right here. We have the sample points and A right here. We extract the subset of long distance pair and we subtract short distance pair. And the result, you can see the point right here. We have a short distance point right here, and the right here is a long pair right here. It means we extract subset R L from A with Euclidean distance. Okay, is predefined upper thresholds, and the set of long distance pair is used for orientation estimation. Right here we use for orientation estimation, but we also extract the pair from A whose Euclidean distance is below lower is short distance. Okay, the subset S right here, short distance pair for the binary descriptor string. Okay, and from long pairs, the key point direction right here, we can vector G can compare right here. We compare gradient strength, we compare key point direction vector G. Okay. And based on vector G, we can use direction of sample pattern to rearrange the short distance pair and ensure rotation invariant. Based on rotation invariant short distance pairs, the final binary descriptor can be constructed. Okay, and the last one, we compute the angle key point direction. We use and try to match short distance pair, and we compare the intensity between all the pair in S. Okay, so after we compare orientation angle of the key point from G, okay, we use it to map the short distance, okay, short distance pairs invariant rotation. Then the intensity between all pairs in the short distance pairs is compared, and use to assemble the binary descriptor we can use for matching. Okay, so in the code you will see right here, this one, the detector right here, the key points, the sample point right here, you have the center of the cycle right here. There is the location and the size of the cycle reflecting the characteristic scale. That's the key point can be seen in the flowing right here, the flowing image right here, with the center of the cycle denoting its location right here. You can have a lot of cycle right here, and the center denoting the cycle location, okay, and the size of the cycle reflecting the characteristic of scale. And in the code, we will try both of the methods. We use HOG and we use the binary descriptor. So which one is faster to get a key point detector and descriptor? Okay. Right now, summarily, we already know about the two things. The first thing we know about the descriptor HOG, and the second one we know about the descriptor, binary descriptor. That's two important things you have to know. And we also know about a little bit what the key point. Okay, I remind you, key point detector is the algorithm that chooses the points from the image based on local maximum of functions such as the cornerness, right, matrix. We saw the Harris detector last video. We know we try the Harris detector, right? We detect the key points, right? And the second thing you have to understand the definition descriptors is the vector value which describes the image path around the key point. There's various techniques range from comparing the raw pixel value to much more sophisticated approaching such as histogram of gradient orientation. Okay, let's remember that descriptors help us to assign similar key point in different paths. How we use descriptor to get the similarity in different batch? Right here, right here, right here, right here. A good descriptor is avoiding mismatch. For example, right one right here. Yeah. Okay, we jump to the little bit of code right here to understand about the how to apply the HOG and apply the another one is binary descriptor to detect the image. Okay, right here the same thing. The important thing you have to import this one into the Visual Studio, and it's a little bit complex. I told you right here because I already did the import the OpenCV 3 or 430 version 430 into the this code. So it takes about 30 minutes to do that. So I wish I do another video to do that, because if I use the video I saw you last time, import the OpenCV, it do not work with the ship method, with the HOG methods right here, because it's not free. Okay, it's not free for us to use. We have to say non-free right here. It means we have to know how to import the OpenCV into the Visual Studio 2019. I will show you later. But anyway, we focus on to the code we have right now. We create the image grade with the type variable is math right here, and we use the IMGrid. We read the image, okay, and right here we convert to the grayscale. It's easy. So like last video, okay? And right now we use the brisk detector and descriptor. It's a hard, right? We use the hard method intensity gradient. And right now we call this vector. Okay, this is really important thing you have to know when we use this include this library. So we call detector brick create right here. Sometimes you can use different method. I mentioned in the right here. We try brick, right? But you can try different. We can because we use brisk right here. We can use brief or brick, KZ. All the methods you can apply. But right now we use the brick right here. Okay, we can change this value into different name right here to try different algorithms and create a key points brick right here. This is a vector type, right? Key points, and we measure the distance from start to finish, how long it takes to get the descriptor and the detector and descriptor. And we use the detect right now. We pass the image and the key points brick vector key point brick right here. Okay, and they show us, we show right here with the CR for us how long it takes and how many key points, okay, and how long it takes. And how about the descriptors for brick? We also use right here, okay, the descriptor extractor, okay, descriptor right here we use brick. In an example, we can change the name right here for different algorithm. I show you. And right here, you remember the descriptor is the match. The variable type is the matrix is okay. It's not a vector. Key points is the vector, but the descriptor is the matrix. And we also calculate how long they take for descriptor. Okay, and we compute. We pass through the image, pass through the key point right here. Verify the key point, and we got the matrix descriptor. Use brick, okay, and we calculate the time, how long it takes. Okay, for using the method brick. Okay, and right here we just visualize the result. We draw the we create the another visualized image clone right here in the copy. This is a copy from the image, right? And we draw the key points onto the image. That's it. Okay, this is the first one. How about the shape? The shape it means they use the house, right? And the bricks right here they use the what? They use the binary descriptor, right? Binary descriptor. And right here the shape you already know they use the US. They use the not binaries. They use the house. Okay. So now we try to compare two methods. Which one is better, faster, okay? And we also use to create a vector key point zip, okay? And we also measure the time how long it takes. We also pass through the call the function in the detector right here, pass through the image and the key point right there. And we show the how long it takes to get the key point. And after that, we also do the same thing, okay? We use the shape descriptor extract right here, and we also create the descriptor use shift, okay, match, okay. Remember right here is the matrix variable is metric, right? It's not a key point, is a vector. And we also calculate the time for descriptor, and we do the same thing, and we call it a main. That's very simple for the code, and you see. The hardest thing right here, you know how to include the OpenCV as Visual 2D right here. And that method is a little bit complex to use the CMake. I show you how to use CMake right here to build up the library, a shape house shape for Visual Studio 2019. Alright, the shape. This is the result. You can say the bridge detector 2019 896 key point in 403 millisecond. Bridge detector the bridge descriptors is about 181 millisecond, but ship they detect only the 1890 key point in 55,000. Okay, 663 millisecond, and you can see ship descriptor 1000 millisecond around there. It's really longer than the bridge. Okay, bridge they use the binary descriptor, right? And ship they use the horse, right? Okay, we already compare right here the bridge result. They create a lot of the key points right here, okay, and the location of the key points. There's a lot of the key points, more than the ship detector right here. You can see ship detector. It's a less key point and it takes longer to detect that. It's not good for real-time application, right? Okay, this result is really cool. And look at the result right here. You can see binary descriptor is good methods for us to do. Okay, alright, see you in the next video. I will show you how to do the install the ship library. Okay, for Studio 2019.